Um. Okay, so the last part of rotational kinematics is the conversion of mass into inertia. So mass is m, and it's measured in kilograms. So what we have to do is find the analogy for mass, and that's inertia. So the equation to get inertia is mass times the radius squared.
Yes, Judah.
You started it.
It was all soft.
I know.
Sorry guys, Kath and Katie had too many shots.
No, trust me, you'll see when I have to have a shot.
So I was gonna get back and be like, guess how many times Homie failed?
So the conversion from
Wait, stop. Okay,
Yeah.
ready, set, go.
Okay, so the last conversion is from mass into the rotational kinematics, which becomes inertia. So inertia is mass times radius squared. So what all we have to know is that if you just take the mass of something and multiply it by the radius, twice, we get its inertia, and that basically means inertia is basically if something has mass. I can't do this for some reason. So the last portion for rotational kinematics is inertia. So in linear kinematics, what we learned was this concept of mass, which was the sum of all pieces of matter that make up a single object. So mass we called kg, or kilograms. So the conversion for kilograms into inertia, which is our analogy for rotational kinematics, was basically this equation. It was inertia is equal to mass times distance squared. Now, this is an average of what inertia actually is. Inertia is different for different types of objects. This is just a general equation for what inertia is actually. So we can also see that if inertia is an analogy to mass, we can use similar equations when we're computing that we use for linear kinematics. So we know the equation linear momentum, which was mass times velocity. Mass times velocity. So if we want to make the analogy for this into rotational kinematic terms, we're going to use the analogies for each one of these variables. So for mass, we have inertia. And for linear velocity, we have angular velocity, which is omega. Now, this is called angular momentum.